Hello everyone. This is a sort of experimental video where I am going to try programming the Mandelbrot set. Well, writing code that will display the Mandelbrot set. Let's see what the Mandelbrot set is. It's this fractal. It looks like this. We're going to program it in JavaScript. Specifically, I have some editor that I made. We can just program it in this editor. We'll just blow this code away. Okay, well, maybe we want to keep some of it. Let's delete most of the code, but we certainly don't need this library. I don't know if we need any library, but there's one library that for the purposes of, let's just do it without a library. It'll be more clear. This body, we could finish it up here. It doesn't matter. Anyways, let's see where we're at this point. I'm going to open up the debugging pane, and here we have hi is being printed out. So we're going to create the Mandelbrot set, and that will require drawing stuff. And a common way of doing that is with a canvas. So we will create a canvas. There is this function called create element canvas, and there's this thing called document.body. It is this thing, and I can append the canvas to the body. Now, well, let's run that. I am pretty sure there's a canvas there. Yeah, there it is. It's the canvas. We can, I don't know, decide how big we want this thing to be. There's a width and height property of a canvas. Let's say 256 units. What does that give us? Okay, we could probably make it bigger. Let's go for 360. Yeah, well, whatever, that'll do. And now, just for fun, I'm going to put a border around it so I can see that it's there. All right, there it is. Sweet, a canvas. Now, in the end, we're going to need to draw pixels onto this canvas. So we might want to figure out how to do that. There are a number of ways. The way the way that I think will work, I think there's something called get image data. There's certainly something called put image data in the land of JavaScript. We really expected that to search more quickly. I wonder if the internet is working. It is. Okay. Here we have put image data. It wants this thing called image data. It is an image data object containing the array of pixel values. We'll need to create one of these things somehow. I've done it before. I have some vague memory of how it is done. I think that you might be able to create an image data. You might. Maybe this thing has some clues for us about how to create one of these. Nope. I mean, yep, maybe. Create image, whatever, image data. Canvas create image data. Huh. Seems like it exists, and it's a method of the canvas. I guess all I needed to do is just trust that that the name was good. Okay, so we're going to create an image data that is the size of our canvas. That is to say, we'll be creating a kind of side canvas. Image data, whatever. And we can draw into this thing in this wacky way. What's going on is that image data is image data dot data, this thing, our image data dot data is an array of bytes, I guess you could say, in groups of 4, and each group of 4 defines a single pixel. The first 3 are the red, green, and blue component, and the last one is the alpha component. So we'll do something like they were doing. We'll iterate over all the pixels. Do just exactly what they're doing at first here to get our feet wet. So I'm gonna make this look the way that I want it to look for whatever reason. Okay. There we go. So we have these we're iterating over every pixel, basically. It looks like we're iterating over every pixel, and we're just setting it to be red. Red is the first one of these things, and we're making the alpha all the way up, which means that we can see the red. So let's say that we created some image data like that and put it on our canvas. You know what? I don't think this is the canvas. I think it's actually the so-called graphics context that has that. Yeah, that's just how they have it set up. There's a different object that you need to pull out of the canvas to get. Anyway, or I'm wrong. We'll see shortly. In any case, I think the graphics context also has put image data. And I think maybe a location to put it, we'll put it in the upper left corner. Okay, well, that did not work. C get graphics, it's not a function. What is the issue here? It is possible that I have the wrong function, or that I spelled it wrong. Oh, I think it's get context. Yeah. Okay, there we are. Now we have a red square. Of course, we want the Mandelbrot set, so we are not finished. But one thing that would be cool to do is, so in the end, we're going to want to draw pixels. Well, the Mandelbrot set is oriented in a two-dimensional space, and its extents are that 0 is somewhere, I don't know where 0 is, somewhere in the middle, like here, and it goes this way about 2 units, and this way about 2 units, and up about 2 units. So it's about a circle of radius 2 around the center. So what we're going to be doing somehow is pretending that all of these points are points in the where 0 is in the center and where 2 is on the side and 2 is up here. I'm trying to think of a thing we can do to convince ourselves that we know how to do that. I'm thinking maybe let's do a circle where we'll just make the color be how far away we are from the center. Okay, so here's the plan. We're going to iterate over, let's go for, we're going to create a couple of for loops, and these for loops will take us over all of the pixels in the square. 360 on this side, 360 down this way. So we'll visit each pixel. Now, when we do, this code here will not be able to look the same anymore because this index I doesn't exist anymore. And so we'll have to do something a little bit more clever. What we can do is say, we have to figure out how big a row of these things is. We want to do y times however big it is. And it is 360 times 4, because there's 360 pixels and each one has 4 things. So that's how big a row is. And then we're going to add where we are in the row, also times 4. We could put this into a variable, I suppose. Maybe we could call that variable I. So now it's the same. We can kind of ensure that we've sort of cut and pasted everything correctly here. You see, now it's green because I moved the 256 from here to here. Okay, so now we want it to be a sort of circle. I'm going to check this recording and make sure that my face is still in it. Okay, well, we have an x and y coordinate in pixel land. Now what we would like to do is create a coordinate in Mandelbrot set land. And let's say that we'll call our x coordinate in Mandelbrot set land xx instead of x. And we want to figure out where we are. Let's see. If we divide by 360, that'll give us, that'll be like, this will be 0 and this will be 1. We could maybe multiply that by, there's a length of 4 across here in total, so maybe we could multiply that by 4. But somehow we want the center to be here instead of here. So at some point here, we're going to want to subtract 2. Maybe we can just do it at the end. So here we have y divided by 360 to give us yy. Same deal. And now we want to make our, I don't know, some value, our color value, intensity, be equal to some function of how far away we are from the center. Our distance from the center, I suppose, is x squared plus y squared, the square root of that is how far we are from the center. And we want to sort of map maybe 0 to a color of 0, and 0 to being 0, and 2 to being the brightest intensity. So the biggest this can be right now is about 2. So maybe we can just say that if it is 2, that'll give us the brightest intensity. Let's do this. 255 divided by 2. So if it is 2, then it will give us 255. However, if the intensity is greater than 255, then we don't want that, so we'll cap it at 255. Also, I think we want this to be an integer. Great. So now this number is something. Let's see what happens. That actually seems like it worked. Great. So now we have some numbers that kind of, in some sense, tell us where we are in Mandelbrot set land. So now we need to figure out what to actually do to know what to draw for the Mandelbrot set. Now the way that it works is it's a very simple function that involves imaginary numbers, and I'm sure it will be in Wikipedia. Let's see. Mandelbrot Wikipedia. Mandelbrot set. Okay, great. Here we are. This thing here. The deal is that we start with a point, and that point is wherever, like, we'll be in this loop. Each time in this loop, we're going to decide what color to draw that spot. And our color options are black in the center. I mean, we could make it different than black if we wanted, but black in the center, and everywhere else some sort of other color. Black means that we're in the Mandelbrot set mathematically. And all these colors, they kind of say how out of the Mandelbrot set you are. You're definitely out if you're a color, but the color says how out you are. And that has to do with this thing. We start at a number, the number wherever we are, and we do this thing over and over again. It will modify our number to be different than it was over and over again, and we keep doing that, and we see if our number ever blows up out of control, which if it ever gets further than a radius of 2 away from the center, it is sure to blow up out of control. So that's kind of why there's a radius of 2 around the Mandelbrot set. Anyway, specifically, the Zn here, you can think of this equation working in the following way. We'll start with a number, and this number is an imaginary number, so it has an x and y component to it, you might say. We'll square that number, which means something for imaginary numbers. We'll have to look up what that is. And then we're going to add c. I think I am wrong. I think c is our number, and I think Zn starts with 0. Yeah, Zn starts with, so this starts with 0, but c is the number that we're at, the point that we are at. So we'll take the point that we are at, and we'll take 0, and we'll square 0, and we'll add our number, and then we'll get some new number, and then we'll square that number, and we'll add our number, and we'll get some new number, and we'll keep doing that. So here we go. we'll make a function, and this function will tell us if we're in the Mandelbrot set. Are we in the Mandelbrot set? I don't think we're allowed to put a question mark at the end of that, unfortunately. And we'll give it an x and y coordinate. Now, what it says is that we're going to have some number called z, and that number is going to start out being 0. Now, that number is an imaginary number, so let's just represent that with an array of 2 numbers, our real and imaginary component. There's also this number called c, and they say that that is our number, so that is going to be xy, the real and imaginary component of our number. Now they want us to square z. They want us to do this somehow. So let's see what it means to square an imaginary number. Square imaginary number. An imaginary number is a complex number, blah, blah, blah. How do we square it? This is a very specific case. If you, the square of -1 is, well, the square of -1 is 1. The square of I is -1. Square root of -1. Okay, we could look this up. I happen to know how to do it. It seems like it may be easier to pull this out of my head than to pull it out of the internet at the moment. The way multiplication works with imaginary numbers is that we have a real component of one number, a real, I guess, and we have an imaginary component of that number times I. And squaring it means that we're going to multiply it by itself. So what we'll be getting here is this real component times the real component plus AR times AI times times I plus AI times I times AR plus AI times I times AI times I. Goodness. So here we have the imaginary number multiplied by itself, or some incarnation of that. Let's call our result here z2. Z squared is going to be AR. That's the real component of our number. That is z0 times AR. That is again the real component of our number. AR. That's the real component. Okay, this is the imaginary component of our number times I. Okay, right. What we're really doing here is creating an imaginary number, and that imaginary number has 2 parts. The real component includes this guy. The imaginary component seems like it probably includes this guy. Let's see here, we have an I again, so that seems like it's on the imaginary part. In this I, we're not actually going to multiply by I. We don't have the number I. We just have real numbers here in computer land. So that's why we're using an array. And this is the second part of the array, and that's what means that there's an I there. AI, that is Z1. AR, that is Z0. Alright, this looks right. Z0 times Z1 plus z1 times z0. There's a certain symmetry there. I'm convinced that that's probably the correct equation. I happen to know that it has a certain, like, 0,1 and then 1,0. And we'll see a similar kind of weird symmetry up here. I claim we put it here even though we have two i's, because multiplied together those things are -1. So really we can put a negative out here, I guess. And we have ai, which is z1. There. All right. So I think there's a good chance that that is, in fact, z squared. Okay. But then we need to add c to it. So I guess we'll say that the new z is going to be z squared real part plus c's real part, and also z squared's imaginary part plus c's imaginary part. Okay, let's do this. So this is going to be in a loop. We'll have to figure out exactly how to operate this loop in a moment. But for now, we know at least that we're going to be, like we start out with z, and we have c here for our use. We get in a loop, and we're going to create, ultimately, we're going to create a new z that is some function of our previous z. And we want to keep looping until something happens. Really, I guess we want to, I mean, we can't ever know that the point is in the Mandelbrot set. All we can do is get more and more sure by running this iteration longer and longer and seeing that it doesn't explode to infinity. So we'll just set some arbitrary cap on how long we'll look. And let's make that amount of time that we look be 255. We'll do that many iterations. That way we can directly map the number of iterations that it takes before it fails to be the color. Because that's how many different colors there are. I mean, that's how many different shades of color there are. For a single color, like green. Now, so this will take us through all of them. We don't actually want to, we want to exit this sometimes. I'm trying to think if we want to exit it at the beginning. I guess we don't need to. I mean, z is always going to be 0 at this point. So at this point here, after we have our first new z, we want to check to make sure that it's close enough to the center, which means that the distance from the center is less than or equal to 2. So to get the distance from the center, we can do the mathematical square root of, well, I guess we can do the real component times itself plus the imaginary component times itself. Now, it is probably fast enough to do this, but in this case, there is a exceedingly clever hack that is faster, and that is to instead of taking the square root of it, since we just want to compare it to some value, we can just compare it to the square of what we were going to compare it to. So we were going to see if this value was less than 2, but since we took away the square root, we'll ask whether it's less than 4. Anyway, if it is less than 4, that's good. So really what we're after is the condition where this is not true. Or I guess maybe we could say it's greater than 4. So if it's greater than 4, that's bad. I mean, it means we're not in the Mandelbrot set. So we can return how many iterations it took to discover that fact. And if we are in the Mandelbrot set, that will happen here, or we'll go through all the iterations and we'll never discover that we're not in the Mandelbrot set. I don't know, maybe we could, let's do -1. That'll mean that we're in the Mandelbrot set. I mean, we could do I, it seems, whatever, it doesn't, there are good reasons for a number of choices for what we return. Anyway, there we go. We have, are we in the Mandelbrot set? Let's see if it works. Let's see where where do we even use this thing? How do we use it? Are we in the Mandelbrot set? It takes an x and a y. I think that x and y is this x and y. And now that'll give us some number, some result. Let's put that into A, this result. And if A is, well, I don't know, if it's -1, then we're in the Mandelbrot set. So if we're in the Mandelbrot set, why don't we just do this? Will be black. And if we are not in the Mandelbrot set, then will be some color. Will be blue. Blue's kind of dark. Let's be green. So A is the number of iterations. Maybe we want like 255 minus A. We'll see how it looks. Maybe we can invert it if it looks bad. Oh man, I'm kind of afraid to run this. Okay, I'm gonna copy this code. My concern is that there's an infinite loop in it somewhere. If there is, then the nature of this editor is that I won't be able to access it anymore. So I'm gonna stash this code away somewhere else so that we can get it in case there's a problem. Whoa, there it is. There's the Mandelbrot set. You can kind of see it there. we can make it more clear that what's going on here. I think if we I mean, it's mostly very dark. We could, what could we do? Well, one thing we could do is this. So now everything's red except the stuff in the Mandelbrot set, and you can see that there's yellow. Maybe red is pretty bright. Maybe if we did blue for this, well, seems like we might want to boost our A value, and we could just we could just add a number to it. What about this? We'll add a number to it, like 100, but we'll still keep it capped. And it's added 200. That's not quite doing what I was hoping. I think we would need to scale it rather than adding a number. Why don't we multiply it like this? Okay, yeah. That's starting to, you can see some color reaching out more and more. Oh, there, that's beautiful. Okay. I approve. So there is a bunch of JavaScript code to draw the Mandelbrot set. Pretty similar. You can totally convince yourself that this is a real thing from that. That's pretty simple code. There it is. All right, great.